Good morning. My name is Charlie Trantanella. Thank you very much for coming this morning to hear a little bit about some of the work we're doing in Custom MMIC in high linearity mixers using GaN technology. So certainly, to probably most people in this room, if not most engineers around the world, when you hear the two words GaN MMIC, the first thought that comes to mind is power amplifiers. Gallium nitride is really the Marshall stack of the amplifier world, and with good reason. You can make some great power amplifiers on GaN, very efficient, very high power, very small, and that's really been the dominant research focus for gallium nitride. But I'm not an amplifier designer, and so one of the things we asked at Custom MMIC is, what else can we do with gallium nitride besides power amplifiers? Because there is more. So what I do design is I design mixers. So the question we asked ourselves is, a GaN MMIC process, it's a MMIC process with a couple of different elements, but we can make all sorts of things on it. So why don't we try to make mixers? We make very good power amplifiers. What about mixers? And in general, mixers have three very important properties. The first two are the same, linearity, and then the last one is really everything else. A mixer, if it's a little lossy, we can overcome that with some extra gain. If it's a little noisy, we can overcome that with an LNA. If it's got some poor isolations, we can sometimes overcome that with filtering. But linearity we're really stuck with. If our mixer generates some intermod products or has a bad compression point, there's really no way to get around that. The nice thing about gallium nitride, though, is it really, to quote Captain Kirk, it offers us the chance to boldly go where no passive mixer has gone before. And our focus really here is on passive mixers as opposed to the active kind. So with MMIC-based mixers, we have two main choices of mixing element. And the nice thing about most of the GaN processes, though not all, that we have access to, is that these GaN processes, again, can support the two major types of passive mixers. The first is a typical, what we call a cold FET. You take the FET as a three-terminal element. You have access to the gain, the drain, and the source. And you put the signals in the right places, and that FET will end up mixing. The other device we can do is we can take the drain and the source of the FET and connect it together right at the device and make a two-terminal diode, Schottky diode. So those are the two main elements, and we're going to look at how both of those mixing devices play in the GaN world. And the nice thing is that they're different. They offer us different choices in terms of topology, in terms of physical layout, and in terms of benefits. And we will see that, again, they do give us some nice things in both areas. So there's, I think, opportunities for both styles of mixer to give us what we want, which is, again, very good linearity. So, one question briefly is, well, why is gallium nitride so much better than what we're used to, which would be typically gas PHEMT in the 3.5 world? And as an example here, take a look at just the typical IV curve of some diodes, and we can again see some physical reasons why GaN is so much better. So on this IV curve, the blue one here is a typical PHEMT diode. This is a 300 micron device that we put through the IV tracer. And what we can see is it has a turn-on voltage of about 0.75, 0.8 volts, where the current really starts going through the diode. And that's fairly typical of most PHEMT processes. You can move that turn-on point a little bit, but you're pretty much around 0.6, 0.7, 0.8 volts. GaN, on the other hand, is a little bit higher. So the red curve represents kind of typical GaN diode from one of the processes we use. This is a 400 micron total periphery. So again, both these are fairly big, but chosen really just to give nice current values. And we can see this one turns on around 1.1 volts, so about 30 or 40% higher than a typical PHEMT diode. The GaN will turn on, and it has a much different slope. So the diode, just from a physical perspective, looks a lot different. From an electrical perspective, there's some differences going on here. It's not just a slightly tuned gas diode. It is really its own unique element. And again, the higher turn-on voltage, it does, we'll see, lead to higher IP3, but it does also mean to LO drive. So nothing is free, and certainly in gallium nitride, that is where we pay the price. It's the LO drive. So a few months ago, back at the IMS in San Francisco, I was fortunate to give a micro lapse on some of the GaN mixers we've done at Custom MMIC, and that was really our second generation GaN mixers where we got input IP3 levels around 30 to 33 dBm pretty consistently. I'm happy to say that what we'll be looking at here today is our third generation sets of designs, and we've really exceeded that IP3 level by quite a bit. So again, the results here have not been shown outside. This is not really just a repeat of the microamps. This is some brand new data. And I'd like to take a look at really 3 examples of some mixers we've done on this third generation. The first is an S-band, again, FET mixer using the 3-terminal device, the cold FET. The second is an X-band double balanced diode-based mixer. So again, looking at a 2-terminal device. And then finally, a high-frequency KU-band GaN FET mixer, again, using the 3-terminal device. So we have 2 3-terminal devices and 1 diode-based mixer. And these were all fabricated on the same process. This is a US-based commercial GaN process. So the first one here is an S-band FET mixer. I've got a little dye photograph of what it was like manufactured. This was designed really to convert an RF frequency range of about 2.6 to 3.8 gigahertz with an IF response DC to about a gigahertz, I believe. And the way this works is the yellow comes in on the left. It goes through a little low-pass filter to the gate of the cold FET, and then encircle the FET there in the middle. The RF comes in on the right. It goes through a little spiral transformer that's actually acting as a diplexer. So it goes through the diplexer and attached to the drain of the FET. The source is grounded. Then the IF is taken off the drain as well through a little kind of a low-pass filter with a band stop element to provide some isolation. So this is not a balanced design. It's just, again, a cold FET with some components around it to kind of massage the performance. And that diplexer and the little band stop filter do provide the isolations of this device. So taking a look at how we did, the first thing we worry about, I know we say linearity is most important, but it's easier to think of a mixer in terms of its conversion gain bandwidth. That's usually where we start when we want to investigate mixers. So what we see here is the conversion gain over an LO frequency range. So we look at from 2 to 4 gigahertz. We have an IF, we used it as a down converter with a fixed IF of 100 megahertz upper sideband. And we see we get a nice bandwidth, again, around 2.6 to 3.8, 4 gigahertz. So fairly typical for this style of mixer. And we approach conversion gain levels of about 7 or 8 dB, which, again, is quite commensurate with what you would see in a gas p-hemp design. So we're not losing a lot in terms of conversion loss by going to GaN. But the one thing we do see is we do need quite a bit of LO drive, whereas a typical gas mixer might need, passive mixer might need 15, 18 dBm. We are well above that. And indeed, this mixer saturates above 20 dBm LO drive. So we need some power. That is the trade-off we make with GaN, but the hope is that we get a little bit more efficiency. So in terms of how we did there, if we look at the input IP3, again, this is the same idea, down converter, a fixed IF of 100 megahertz, upper sideband, sweeping the LO frequency and looking at a bunch of different power levels here. We see that our input IP3 is, again, quite high, between 35 and 40, sometimes eclipsing 40 dBm, and across the 1 gigahertz bandwidth, which is very nice. And if we think about, linear efficiency, for most mixers, pretty much the input IP3 is around what the LO drive level is, maybe a couple dB higher. Here we're about 8 to 10 to 12 dB above our LO drive is our IP3. So we've got some nice linear efficiency going on. So we do have to drive this mixer quite hard, but we get the benefit back of very, very high input IP3s. So again, it's always a trade-off, but that's a nice trade-off to have. Yes, we've increased the LO drive, but we've gotten a lot more bang for our IP3 buck in that case. So the second one to look at is an X-band double balanced diode mixer. This was designed really to cover a RF bandwidth of about 7 to 13 gigahertz with an IF response, again, DC to 1.5 gigahertz for this particular project. So fairly typically, the LO comes in on the left and goes through a spiral transformer balun. The RF comes in on the right, single-ended, and goes through a spiral transformer balun to get our 2 balanced signals. Those are connected to a ring of 4 diodes, GaN diodes here, which are marked by the red arrows. Then the IF is taken from the center tab of the RF balun and comes through a little low-pass filter. We actually added a spiral inductor there in the IF port to tune up our IF bandwidth response and get some good return loss. So that inductor is, sometimes it's there, it's not always required. This particular project, we wanted to limit the IF bandwidth. And again, this design, there is quite a bit of extra space on the side. The yellow and RF, there's those bright gold traces are as the bond paths were pushed out. That was really just a manifest of the way the reticle came together. This could be shrunk a little bit smaller, but as you know, when you put reticles together, you don't have infinite choices for sizes, so this had to fit in a certain size, and so the bond paths kind of moved out. But that's not a requirement of these kinds of designs. So again, starting, if we take a look at what the bandwidth of this mixer looks like in terms of the conversion gain, again, we've measured this as a down converter with a fixed IF, again, of 100 megahertz. In this case, it was lower sideband. We swept the yellow between 6 and 13 gigahertz, and what we see is that eventually when we drive it hard enough, we get again 7 to 8 dB conversion loss across a nice band. This does have a little bit of slope to the conversion gain, and this is really an artifact of how this was measured. This was measured on wafer without bond wires, whereas this die was actually designed to go in a package. And I do have them in packages. They're sitting on my desk. I didn't get a chance to measure it before this talk, but we expect that gain to flatten out with the bond wire present. But what we do notice, again, our conversion gain saturates at much higher LO drives than we're kind of typically used to seeing for a gas P-hemp-based passive mixer. We have to drive this about 20 dBm or higher to get the nice flat saturated conversion gain. So with the FET, we saw a high LO drive, and the same thing with the diode, but we expected that, and the hope is that we did get some payoff. And indeed, in terms of the input IP3, the linearity, we did see that payoff. So here, again, same conditions, sweep the LO frequency, fix the IF at 100 megahertz lower sideband for a down converter. What we see for our IP3, input IP3 is typically between 30 and about 38 dBm across the band. We get a nice about 2 gig bandwidth where that IP3 really peaked up. And if we drive it at 26, 27 dBm, again, we're approaching 40 dBm input IP3 for a diode mixer, which is very good. It's obviously not across the full band, but this, like I said, was our third generation, and we've increased this from our second generation by about 8 dB. So the hope is to flatten this out and get this even higher, but it's certainly a nice start. The last mixer to look at today is our highest frequency one. This is a KU band FET mixer. Again, we went back to the FET design, the 3-terminal mixing device here, just as an alternative topology. This one is very straightforward. The FET there is in the middle. The yellow comes in on the left through a little low-pass filter onto the gate. The RF comes in on the right through a high-pass filter right onto the drain. The source, again, is grounded, and then the IF is taken off the drain through a low-pass filter. So it's there's no balance here. There's no transformers. We got rid of the spiral transformer diplexer and just went with a low-pass, high-pass filter kind of diplexer. And that's really where we get our isolations from. There's no inherent balance here, so isolations are really provided by those on-chip elements, the spiral inductors and the capacitors. So first, to take a look at the bandwidth, again, we have the conversion gain here is a down converter, sweeping the LO 13 to 19 gigahertz, 100 megahertz IF frequency for sideband. And what we see is when we get up to finally close to being saturated, we're getting about 9 or 10 dB conversion loss, so a little bit higher than the previous two mixers. And that's really a consequence of having to use a smaller device at these frequencies. As the frequency goes up, these mixing devices want to get smaller to handle the bandwidth, and when they get smaller, they have higher resistance values, so that comes into play here with the conversion gain. But we do see that very nice flat response as we drive it hard enough. We drove this up to 24 dBm. I would have liked to have gone higher, but our lab equipment kind of stopped there. So generating power at that frequencies in the lab can always be a challenge. So I think if you could drive this a little bit harder, maybe up to 27 dBm, you might get flat 8.5, 9 dB conversion loss across the band. But we certainly have not saturated this. Then in terms of the input IP3, we see a very similar looking curve to the conversion gain, again over the same LO frequency range. As we drive it harder, that input IP3 just keeps creeping up to about 33 to 35 dBm across the band, giving us again a nice linear efficiency of about 8, 9 dB above the LO drive. So again, driven pretty hard at 26 dBm, but we get a lot of bang for that. We get up to 35 dBm for an input IP3. So it just, again, in conclusion here, what we like to say, what we like to think is that GaN has really offered passive mixers the chance to reset the bar for what input IP3 levels can be expected. About 10, 15 years ago, when I was designing mixers, the goal was really to get to input IP3s of 30. And a lot of people have done that, and now really what we hear a lot is, can we get to 40? 40 is the new 30. Mm-hmm. And we think the way to get there is with passive gallium nitride mixers. In general, the FET-based, the 3-terminal mixing devices have higher IP3 than the diode designs, but the trade-off, again, is in isolations, which I didn't get to show, but I certainly have lots of data showing that the double balanced has the best isolations. It has a lot better spur performance, but the FET one will give you that raw intermodulation performance, which, again, in some applications, that's what you care about most. So we mentioned everything comes at a price, and for the GaN mixers, the one thing they do need is LO drive. So the solution, which we're working on right now, is to take advantage of what the GaN process offers us, and that is a chance to make Marshall stack power amplifiers. So the idea is really to take our mixer and take one of a power amp or drive ramp and marry the two up and generate a mixer that has reasonable LO drive levels, some on-chip amplification, and then the very high input IP3s. So that's kind of the next place to go. It's the next logical progression. And again, it's someday, maybe we'll say 50 is the new 40. But yeah, thank you very much. Yes?
Yeah, I had just a couple of questions.
Sure.
So on the diode one, you're still using a finger FET with just, you said, the source and the drain shorted. Is there some advantage to retaining the finger FET transistor and trying to make it into a diode as opposed to a circular geometry or some other sort of geometry for the diode? And the second question, so the diode thing. The second question is on the modeling. You have a very low RF coming in. You have a very high 26 LO. Are you using small signal, large signal models? How are you doing the haircut? Are you doing, how do you handle the modeling?
Great question. So the first on the physical makeup of the diode, we're at the mercy of the foundry. We're a fabless semiconductor house, so we contract out our manufacturing to the foundry, and they give us the rules about how they make their devices. So some foundries make diodes, vertical structure with the rectangular contact area. In this case, this is what the foundry says we can do. We're not allowed to do anything else. They certainly won't guarantee it. So this is again, this particular foundry, they make FETs with gate stripes, and so that's how we make the diode. In terms of simulation, we rely mostly on harmonic balance. So we use Agilent, our Keysight ADS, AWR is a similar tool, but you're right, it's harmonic balance. It's small signal really gets you nowhere. Simulation, you have to go to harmonic balance and that kind of approach.
Really excellent paper.
Thank you.
Just to continue that thought, I don't think I saw any simulation results.
No, I did not put any.
So how'd that go? You use the foundry PDK, right?
Yes and no. For the FETs, we use the models that were provided by the foundry. For the diodes, I made my own. We had some test coupons, and I made my own model. I didn't show I've actually done a lot of backfitting on these, and we did very good. We got the bandwidths that we wanted on this. We got the IP3s actually came out a little bit better than we had simulated. Certainly for the FET mixers. The problem with the PDK is we're not allowed to look at the FET model. It's just a black box, so we're at the mercy of what the foundry did. And in terms of, the foundry had made the models for power amplifiers. We were using it as a mixer. And it gave us the bandwidth very well, but the IP3 simulated a little bit lower than we measured. So that was a nice surprise.
What prevents you from going to 30 dBm on a LO drive?
In theory, nothing. In reality, our lab equipment.
Oh, sorry. That's fair.
Yeah, just the current set of lab equipment we have we can generate about 1 watt, but as soon as you add a cable and things that get to higher frequencies, you really lose it. I've used TWTs in the past. We just don't have that kind of equipment right now. That would be we could get, if we had the equipment, we could go there and yes.
Have you experimented with anything beyond KU band at all?
For the GaN mixers, no, we have not gone beyond KU band. Part of the issue that this process, it's what we like to call a landed metal process. So the air bridges are quite limited. When you land the metal on the substrate, you're kind of limited with frequency range of some of these components, especially the spiral transformers. So getting up above, certainly above this X-band design is about as high as we can go with the spiral transformers. The FET, we could probably go higher, but as that device gets smaller, we get a lot more conversion loss.
Mm.
So you mentioned that the LO drive that you were going to plan to boost that up. So have you done that yet? Or?
Right. In terms of the LO drive, what we have done is we have designed a number and made a number of power amplifiers and driver amplifiers standalone on gallium nitride. We have our mixer standalone, and so the next is to put them both on the same MMIC.
Will that sacrifice your IP3 at some point because of the drive has its own limitations, right?
Right. The answer is it might, but hopefully if we can predict that, we can hopefully design around it by using some kind of wave shaping or matching structure between the two to really optimize. In the past, what I've done when I've integrated gas p-hemp amplifiers with mixers is been able to overcome those problems. You marry the two together, and they actually can work quite well if you have good models and good simulation. Then you can overcome those and get a very nice result.
Will be an advantage if you use a square wave for the LO instead of the sine wave?
Right, so the question is the shape of the LO form, square versus sine. Again, in theory, there could be. Again, what we find in the double balance in this diode mixer, especially because we have a ring of diodes and it's going to clip the LO waveform, you generate a quasi-square wave in that ring. So going to an LO square wave here doesn't buy you much. On the 3-terminal FET devices, it can. Certainly, we've seen a little bit of that, but that would be something we could maybe take advantage of when integrating the LO amplifier.
So just following up this thing, if you had an integrated LO amp, would it help or would it hurt your phase noise performance?
That's a very good question. I would say, in general, would probably hurt it. The question is how much. We certainly know that gallium nitride, the phase noise of the amplifiers is not as good as something like an HBT, and you're going to see that in the mix. So, but again, in some cases, it's still okay. Certainly, in some very high precision applications, you need that low phase noise. Gallium nitride in general is not going to get that for you.
How many years have you been there? I mean, the company.
The company. So we are 10 years old. We had our 10-year anniversary back in May.
So are these ready available or in package?
So as these, right, we have I believe we have 2 wafers worth of these. So we have at least a couple hundred of each of these designs, and I have packaged up all 3 of these. They're sitting on my desk. I've got 50 of each, I think, to test as the first prototype. But we have plenty of die, and we have packaged parts in much smaller quantities. But as soon as we send more die out, we can have more packaged parts.
What type of packages are you using?
These are we're looking at right now the kind of air cavity ceramic package, the Colorado Microcircuits style. I believe you can also, especially the S-band one, we could also put in plastic, but some of the higher frequency ones, we like that air cavity package much better.
Charles, it seems like one thing you didn't mention was sensitivity to or improved tolerance to power in the input, right? I think these would be less likely to blow the mixer, high power spike, or
That's true, yes.
and also like maybe compression or like look at that at all. That would be interesting.
Yeah, that's a very good point. What the power handling of the devices is certainly greater than some of the gas stuff, and the maximum power we can handle is higher than typically the P1 dB of these is about 8 to 10 dB below the IP3.
Okay, did you look at that?
Yes.
Mm-hmm.
Have you done any aging tests on them?
No, these are too new.
No, okay.
But no, we haven't.
Do you have any expectations on aging, I guess, compared to how GaN PAs age and a lot of the stuff that some foundries done, like Triquint, when they did a lot of accelerated aging tests, they saw some really good mean time between failures with their GaN PAs.
Right. I would think because these are passive, we're not running bias through them continually. I think we're not going to see some of these are. I think we're going to see fairly typical performances of what you get now at a gallium arsenide in terms of those kind of, as long as you don't overdrive them, and they should. Thermally, they even if you ran these continually at the nominal LO drive, you wouldn't get anywhere near the junction temperature you needed to burn these out. So.
I gotta ask you one more. You can buy a 32 dBm, silicon-based, whatever, mixer. So the question is, if somebody walks up to you and say, look, why is GaN so good for a mixer? What I heard today is because it has a higher cutoff. Forget about breakdown at 600 volts, forget all that stuff. So if you have a kick in at 1.4 volts and a slope that's less, does that really translate to higher TOI? Why don't I just back bias a Schottky diode, give myself a 1.4 volt turn on voltage and get the same result? Why don't I use a silicon pin, and with a slope?
You're right, and those are very good questions, very valid questions. I think you could, and there are certainly some, like I said, some silicon processes you can control that turn on voltage, or you can stack. If you take two gas PHEM diodes and stack them, you'll get a much higher turn on voltage. And we've done that, and the GaN gives a much better what we call linear efficiency. That IP3 over LO drive is that ratio is higher. I don't fully understand why, but that's one of the advantages. You get more IP3 for your LO drive than you do with some of these other technologies. And the physics of the device certainly comes into play, and that's.
Still looking for that.
Yeah, right. And even if you did take the silicon one and create this high turn on voltage, you still got to provide the power somehow, and it's not always maybe efficient at the frequency you're at to do that in silicon or CMOS. Whereas we can get very efficient amplifiers, driver amplifiers, and gallium nitride to go along with that. So from an efficiency point of view, in many cases, that's where GaN really can win. From the brute IP3 approach, you're right there. There are other ways of getting it, but can you do it efficiently?
Well, then wouldn't it make sense to compare the IP3?
It's been my experience that for passive mixers, 6, 7, 8 dB conversion loss is fairly typical. So if they all have about the same conversion loss, then they put out output IP3, kind of compare 1 to 1.
But in your KU band mixer, you had 10, 11, 12 dB loss, which is substantially higher.
Right, but I'm also not convinced we've reached what the actual limit we could get if we drove that hard. You're right, and 9 dB versus 7 dB conversion loss, your output IP3 is 2 dB lower. But the industry has kind of, for passive mixers, has focused on input as the number, whether the conversion loss is 6 or 10. It's always the input IP3 number that gets put on the data sheet, for better or for worse.
Well, the other way to answer that is, they cheat. When you see positive, not you, when you see positive conversion gain, it's because they have an IF amp after the passive mixer on the chip. Oh yeah, I got plus 15 dB conversion gain. No, you don't. You have an IF amp in there, and it's going to cause you undercharges.
Thank you very much.